today's speaker, Professor Dorette Pronk from Dalhousie University, who will be speaking to us about her work on Orbispace mapping objects. The title of our talk is Orbispace mapping objects, exponentials, and enrichments. Just quickly, as always, if at any point anyone wishes to ask a question, you can do so by unmuting yourself or by writing the question in the chat. In that case, we will ask the question for you. Yeah, please, Dorette, take it away. Thank you very much.
Okay, well, thank you all for attending the seminar today. And yeah, as Juan said already, if anybody has a question, feel free to interrupt. I'm happy to answer as I'm going. So this is about joint work with Laura Skoll. And I should say that the beginning of the work was even joined with a larger group of women as part of the very first Women in Topology meeting at the Banff Center. I didn't put the whole list on there because most of what I'm talking about today is from after that time, but it was what started our interest in this work. And so let's see. So I will first just tell you guys what Orbispaces are, or at least our way of looking at them, and then what the morphisms are between them, and turn that into mapping objects that we will show that have both the property that are exponentials, and they give the ability to see orbifolds as enriched actually over themselves. So let's see how far we get. And I should say my list of the contents didn't give this, but I hope to give you a couple of nice examples at the end as well. So informally, an Orbispace or orbifold, as Thurston used to call them, is a Hausdorff space with an atlas of charts. Now, and Thurston talked about them, and actually originally they were introduced by Setake in the 50s. They were given as really a generalization of manifolds in the sense that the charts had to be open subsets of Rn with then the local structure of a group action and a finite group action, I should say. And of course, those are still good examples. And actually, these slides won't give you any examples that are not of that kind. But I just want to say that what we're doing can be applied to a larger class of Orbispaces. If you have some other ones that you might be interested in, then that would work too. Also, that way, I don't have to worry too much at the end about saying, well, this is a generalized Orbispace when it comes to the mapping spaces. Although it's slightly generalized because the Orbispaces I want to work with, that I'm going to take the mapping spaces for, have to be paracompact and locally compact. And because I'm not going to try to get everything completely compact closed, our mapping spaces will not have that property, of course. And you would have to go KFI topology if you wanted to get something that was where the mapping spaces are exactly the same kind of things that you started out with. We didn't want to worry about that. So we'll assume that our Orbispaces we start out with are locally compact and paracompact, but the mapping spaces will just have the properties of being represented by a certain kind of groupoids that we will get to in a moment. So first of all, the informal definition is then charts with local structure. And the local structure, as I said, would be that of a Hausdorff space with a finite group acting on it. And if you think in 2 dimensions, the kind of things you might expect to see are rotations, reflections, and dihedral groups. And then now, how do these charts then work as charts for my space? That is by the fact that the quotients of the charts by the group action give us an open subset of the space. And so this allows us for a certain kind of singularities. That was kind of the idea when Setake introduced them. And I should then quickly say something, and I'm not going to use today, but every orbifold can also be described as a quotient of a space with the action of a compact Lie group with finite isotropy groups. Although in general, that space might be of a much higher dimension than the Orbispace you're actually interested in. So kind of slight, small warning there. It's sometimes convenient to be able to use this if you want a particular kind of representations for your Orbispaces, but be aware that there is a bit of an axiom of choice involved there and things like that. Okay, we'll stay low dimensional here today. And our first example is given through the artwork of MC Escher with what we call the triangular billiard table. I had originally planned to put the regular billiard table in there as well. I forgot to do that, but it will show up at the end of the talk. So in the triangular billiard table, what we have is, so whenever you take a wallpaper group, by the way, and you want to find the corresponding orbifold, then you can just look for an domain here that's kind of contains the whole picture. And if the group is generated by the just by the reflections, then things are easy. If you have some rotations in there, then you need to do some further folding to get your orbifold. But here, this one is fairly straightforward. We end up with just a triangle, as I gave here. And so at each of the corners, we have a dihedral group of order 6. And so if you wanted to give this as a chart, then you would, the chart for this corner, the blue part here, oh wait, let me just get my, would be just a disk, open disk with the action of a dihedral group on it. And the overlaps of the charts in this case would have the, could be given as charts with a Z2 action, just a reflection. So this is very nice. In general, the overlaps are often a little harder to describe. And so this is one reason why orbifold atlases are a bit of a pain to work with. They're good to just give the atlas, but when you try to describe maps in terms of atlases, then things can get quite messy. As can be seen from the fact that Setake wrote 2 papers, one in 56 and one in 57 on Orbispaces, or he called them V-manifolds, and they had different notions of maps between them. And neither one of those is the one that we are working with today. Although his maps had some interesting properties too. So the teardrop orbifold is another one that will often be considered by people. It's a good counterexample for many things. And it's just a sphere with an open, with one cone point that can then be given by a chart, as I indicated here, an open subset of R2 with Z2 action, and then for the rest we can use trivial charts to cover the rest of the sphere. So as I said, describing maps between Orbispaces in terms of these atlases becomes quite painful. You have to be very careful, and there's a lot of bookkeeping. And so in my thesis work, actually, I introduced the notion of a topological groupoid as a way of representing Orbispaces or orbifolds. And so if we do Orbispaces, then I don't have to worry about the smooth structure, which I will therefore do today. So topological groupoid is just an internal groupoid in the category of topological spaces. We want them to be Hausdorff, and most of the time we'll want them to be also paracompact or locally compact, but not all of the time. So here I won't say that yet. So in my thesis, I showed that Orbispaces can then be represented precisely by groupoids that are proper and étale. Now I should say every proper étale groupoid represents an orbifold, and every orbifold can be represented by one, but those are not the only groupoids that people may want to work with. So once I get a little further down and I talk about Morita equivalence, you are allowed to take a larger class of topological groupoids and take everybody who is Morita equivalent to one of these. And those are still good representations as well. And depending on what you want to do, you may want to use those or not. Today, I am mostly not going to use anything besides just the proper étale ones. So proper means that the combined source target map from the space of arrows to the product of the space of objects with itself is closed with compact fibers, and that's the source map of the groupoid is étal. However, if the source map is étal, that actually means that all the structure maps are étal because it's a groupoid. If you had an internal category, that would not be true, but for groupoids, that is the case. Okay, then let me give a couple of examples of what can these groupoids look like. Whenever you have a discrete group G acting on a space X, you could make a translation groupoid that has the space of objects to be just X, so it's G naught. And then really what's happening here is that we get for the space, so let's say I represent X by just a disk or so, then G times X is just a bunch of copies of X here, one copy for every group element. And the source just is the projection down, and the target is given by the action. And then multiplication comes automatically with the group multiplication. And in some sense, you can think of the Orbispace groupoids as kind of co-limits of these things. You just need to glue them together for the different chart. For every chart, you would have one of those, and then you need to do something to show how the charts are connected to each other. So here are a couple of examples. I can take this, just the one sphere and have Z2 action by reflection, where we would have two fixed points. So this point and that point. And so the quotient space or the underlying space of this orbifold would of course end up just being an interval. Sorry, that doesn't look very nice, but with two special endpoints, because those were coming from reflection. So we'll often call them silvered endpoints. Come on. Okay. And so I'm going to give you some more examples a little further down. So groupoid homomorphisms would also be maps between orbifolds, of course. So what are groupoid homomorphisms? They are internal functors. So you have a continuous map from G0 to H0 and a continuous map from G1 to H1, so that's the usual diagram commute. So sources go to sources, targets go to targets, and units are preserved, and multiplication is preserved. Let me say one little thing here right away. Because the units just give you an inclusion from G0 into G1, if I give you a phi1 with the property that it does this, that it commutes with the multiplication, then phi naught is a given. So, so you could say that groupoid homomorphisms are actually, I can completely determine by the phi1, and that makes it a little easier when I want to put a topology on them. So that's why I want to say that for a moment. However, as far as Orbispaces are concerned, these are not enough yet. So let me give you some examples as to where that goes wrong. So first of all, I had already indicated earlier, manifolds are, of course, an example of orbifolds, because you would just have charts that are open subsets of Rn, but with trivial group acting on them, and or anything that will give you just free group actions without fixed points will also give you a manifold at the end of the day. Now, a quick way to represent a manifold by a groupoid is to just take both the space of objects and the space of arrows to be a manifold itself. And in that case, even the pairs of arrows just is again the manifold itself, at least isomorphic to it. And because you only have identity arrows, basically, it's everything is easy. So you can think of these M's as just unit arrows on this one, and also all the structure maps are actually identities in this case. So, but I can also, if I have an atlas for a manifold, I can represent it by a groupoid by taking the disjoint union of the charts of the atlas and that would be the space of objects. And for the space of arrows, I would take the disjoint union of the intersections of those charts. And of course, I'm slightly sloppy here. This is the intersection in the underlying space. And then you can see that intersection as living inside each one of the U's, the U1 and the U2, and there's a transition map and so on. So everything works out there. So now if I compare these two groupoids for the same manifold, it's clear that I could send, there's a nice map going this way from the disjoint union to M, because you can send every chart exactly to where it belongs in my space. But going the other way is problematic because topology doesn't allow you to break things. And so what we do see though in this case is that this map from the disjoint union to M would be surjective, and the local structure is still exactly the same in the sense that here there was only one map from any point to itself. But here there's, if I take 2 points that will go to the same point in M, there's precisely one morphism between them. So it's the same local structure. And these two things are important in defining what we are going to call an essential equivalence. So this is a notion that generalizes the notion of equivalence between categories. If you have read MacLean's book, you know that those are functors that are essentially surjective on objects and fully faithful. And we're going to get an internal version of those. So if you want to see another case where this happens, if I can give you a different presentation for the silvered interval. So we had seen earlier that interval with silvered endpoints, that was what I would get from the circle by an action of reflection. I can also do that in terms of charts, of course. And what you would get is we would have the middle part of the interval with just a trivial chart, so chart without any group action. And then for each of the left-hand side and the right-hand side, you could make a small chart with the Z2 group action. So we have the action groupoid sitting here and there for the two endpoints. And then we need some smaller charts to basically go back and forth, or smaller pieces in the arrow space to glue things. So let's look here at the right part here. This needs to be glued to both the left-hand side and the right-hand side of that chart here. So there are here two sets of intervals for that, one to go to the left from the right, one from the right to the left, and then we have everything. Okay, so now again, think about this groupoid and the action groupoid, and you see that I can go from here to the action groupoid, even in more than one way, but they are isomorphic. At least if I do it in a way that, you know, is kind of faithful to what I want, but I can't go back. And now we'll see that, of course, if you go to the action groupoid with this one here, let me just draw it here, just to draw the space of objects. If I would want to go from this space of objects to that one, what would happen is that I can take the green part and send it to the right, and the orange part and send it to the right. Okay, the right and the other one was left. And the purple part, I have a choice. I could send it to the top or the bottom. And so let's say send it to the bottom. So you might think, oh, now you're not surjective, but any point here is isomorphic to a point there in the groupoid. So I'm not a surjective, but I am surjective on objects. Sorry, I meant essentially surjective on objects. So it's surjective on the orbits, so to say. Okay, so again, this is then going to be an example of what I will call an essential equivalence in a moment. So a morphism is an essential equivalence when it is essentially surjective and fully faithful in the following version of things. So for essentially surjective, this is what I said, it's surjective on orbits, but because we're working in topology, we're going to put one extra condition on it. We also want that this map that would show you that you are surjective once you take a combination of a point here in G0 in the domain with an arrow in the codomain. So an X and now going into some Y. So the fact that you can reach all Y's by an X and an H, it's living here, that needs to not just be surjection, but it needs to be an open surjection. So this is the extra thing that we ask for. Now, if our groupoids are étale, which I said I want them to be, then that is actually equivalent to asking that this map be surjective and that phi not be open. So the combination being open is equivalent to phi not being open. So that's an easy way to check that you have the right thing there. And then the fully faithful parts can be very nicely represented by this, requiring that this is a pullback. That was observed by Bunger and Paré a long time ago. Okay, so I will say the two groupoids are Morita equivalents if they are connected by zigzag paths of these essential equivalences. And by the way, so you might think, oh, Morita equivalence, I know that from rings and modules. There is a notion in terms of groupoids, in terms of modules, and that is equivalent to this one, but I won't go into that today. But what I do want to say is that this zigzag can be shortened. You can either turn it into a span or a cospan. So, and both are convenient from time to time. So to get the span, you just take repeated pullbacks, actually pseudo pullbacks, and essential equivalences are stable on the pseudo pullback and along any arrow actually. And so this would give you the shorter version. It turns out you cannot say that they are stable on this push out because actually orbifolds don't like push outs that much. But if you take a push out of two essential equivalences, that push out is an orbifold again, and the push out arrows, so the arrows on the other side are again essential equivalences. So you just stay within the representations of the same orbifolds. And so we can also do it with a cospan. Okay, so the essential equivalences satisfy all the nice properties that you would need to make a calculus of fractions, well, a two-dimensional version of that. And so rather than going into the details about why they do that, because we want to go somewhere else, I'm just going to tell you what I get as my resulting bicategory. So the arrows will be spans where the left-hand arrow, so the epsilon, is an essential equivalence, and the right-hand arrow is just an arbitrary morphism. So the way I like to think about that is that G primes just lets me choose the right representation of the Orbispace so that I can define my map. And then, so now I'm going to do something that those of you who have seen bicategories of fractions before might be like, hey, that's not the same thing that I was expecting. Normally we say that two cells are diagrams of this form, but then we actually say that they are equivalence classes of such diagrams. Now, it turns out that essential equivalences are so nice that you can choose any left-hand side for your diagram, and every two cell will be representable in terms of that particular left-hand side. So I am thinking of the guy in the middle there as the one that lets you talk about the two cells between those two particular arrows. And since I can choose anything I like, I have my favorites. I'll take the pseudo pullbacks today. And so that's why I'm saying two cell diagrams are diagrams of this form. So normally for arbitrary bicategories of fractions, you have to be careful with this because you might have more than one representation of the same two cell with a particular left-hand side, or you might have not all representations with that particular left-hand side, but neither one of those problems occurs for Orbispaces and essential equivalences. So here everything is nice. Okay, so we have only one problem left. There are too many. There are too many arrows from a particular G to a particular H. So in particular, if you are kind of silly and you take 1 point space, then I can, all the essential equivalences over it would form the full category of sets. And of course, that's not a set anymore. And so we need to make this a bit smaller. And so what we will do is we'll find a weakly initial class of arrows of the essential equivalences that will then give us an equivalent bicategory of fractions, but where the homes are small. Because why would you take so many repeats of the 1 point? Don't do it. So we just need to make sure that doesn't happen. Okay, so the weakly initial class is what we call essential covering maps. And what's actually nice about these is that I also understand them a lot better than when I take all essential equivalences. Because the essential covering maps, I kind of feel a lot like taking just atlases that fits my whatever I need to do with a particular Orbispace. So what do? An essential covering map is given by taking a locally finite, this is how I'm making things small today. You can also just say non-repeating, that's okay too. But just because this will be quicker, I'll say a locally finite collection of open subset of G0 doesn't have to cover G0, but it needs to meet every orbit. So the idea is it covers the quotient space. So I take open subsets of G0, meet every orbit. Now if I take the disjoint union of that, then it has a canonical map into G0, of course, and that map will be essentially surjective. Of course, it's open and it meets every orbit, so you are essentially surjective so far. I haven't done the arrows yet. What do we do for that? Well, we just take the pullback because that will give me the fully faithful part. So I basically built the map to be an essential equivalence. And so I now have only one little issue left, and that is that I need my class of maps to be closed under isomorphism. So just take everybody who is isomorphic to these. And that will still give me what I call small over G kind of class of arrows, because for any G, you just have to deal with a subset of the power set, and then the isomorphic 2 has to do with just the space G1. So we're still working with, at most, G1 cross that set, which is still set. It's not even that much, but you know, it's clearly you're still set here. Okay, so if we take the covering maps over G, we are small, and if your groupoids are power compact, then those locally finite covers will exist. And furthermore, they will always, for every essential equivalence epsilon, there will be a U, so that G upper star U, and that should have been an epsilon U. Anyway, it doesn't matter. The corresponding map into G factors through epsilon. So this is what we call, this class here is weakly initial among all the essential equivalences. That's enough to get an equivalent bicategory of fractions. So so we get that if I take proprietile groupoids and I invert the essential equivalent, so the essential covering maps, I get equivalent bicategory of fractions, and this one has home categories that are small. So I can make an attempt to put a topology on that. Okay, so what do we want from that topology? We may want to quickly take a step back and say, what is the requirement? What would I like to see here? Because if you look at the stack literature, they usually only focus on the first point. They want to make the mapping stack, as they call them, then exponentiable. So I want an object that looks like my other objects, and it gives me basically a right adjoint to the product. And because adjoints are defined up to isomorphism, this will actually determine the mapping space or the mapping object up to Morita equivalence. Another thing you might like to do is to get bi-categorical enrichment, and which would mean that you need a morphism from the product of these mapping objects to kind of correspond to the composition, and that needs to be the right kind of morphism here. Now that one has actually loads of solutions. I mean, you can go for trivial stuff like the trivial topology or the discrete topology, both will do it too. Not the solutions we want. Actually, what we want is that whatever we get here would also work here. And we need to be a little careful for that. So let me see if it's my next slide. Yeah, my next slide is what I hope it is. Okay. So if you're interested in knowing what they have done for stacks, Dave Karjady and Birang Nui have most of the results there. But they went for a slightly larger class of things, and they explicitly mention, okay, Orbispaces work too, but Chen did it. Now, if you look at Chen's paper, he did it, but he did not do this in terms of our groupoids. And he actually explicitly says in the introduction that it would be nice if this could be done in terms of groupoids. He wrote this before groupoids had been studied in a lot of detail yet. And because of his representation for Orbispaces, which is still close at least to atlases, there's a lot of bookkeeping that he needs to do. So our first goal when we started working on this was really to write the groupoid version of Chen's paper. And so that's what we're doing now. And but Chen did look at enrichment. He's the only one who actually considered the notion of enrichment, but couldn't do it in terms of the groupoids. So he actually looked at the quotient spaces and noted that the composition gives a continuous map between quotient spaces. So in that sense, we're able to, as we will see, improve on Chen's results. We had to be a little cautious with that. So you'll see there's a little thing you have to deal with before you can do it. Okay, so topological groupoids have both of these properties. And so, as I said earlier, I want to give them a topology, GMAP, a topology by, well, okay, I should actually be a little more careful. This is not entirely correct. I meant to say that GMAP 0 can be seen as a subspace of map G1, H1. Of course, for GMAP 1, that is, so if you do this with the 1, that is a subspace of map of G0 into H1, because natural transformations are represented by maps from the space of objects to the space of arrows. So, but then that way you get a mapping groupoids, and they have both of these properties. They give you a right adjoint to the product, and they give you also enrichment. So topological groupoids, locally compact. You can say it gives you, well, so the only issue is that you don't do K-ified topology, but these two things work. So if we then want to go from doing this for GMAP to OMAP, as I'm going to call it, we need to go from the HOMs of the two category that you started out with, or the bi-category you started out with, to the HOMs of the new bi-category. And together with Pablo Bustillo and Martin Seelt, we have been doing this. We've been studying this a bit in terms of just the set-based category, so not topological. And we've seen there that the HOM in the bi-category is a two-filtered pseudo-co-limit of the HOM categories in the original bi-category. And that is then the result that I want to try to now put a topology on. So let's take this pseudo-co-limit in the category of the topological groupoids. So that means if I'm wanting to go from K to G, I am going to look for the co-limits of topological groupoids of so GMAP I guess I should have written G map here, sorry. From K upper star U into G. And for each one of those, and then this stuff is part of the indexing of that. And so now I should say quickly, the indexing, because the indexing happens outside of the category of topological groupoids, I mean, these alpha and so on, these are, they are not groupoids themselves, so to say. So, and actually, I won't even know how to index topologically. So what's actually happening here is that this part is gonna all be considered discrete by the time we need to do the co-limit. And it works out, I mean, I checked, doing it discrete actually does exactly give you a co-limit. I mean, you can show that it is the co-limit at the end of the day. Okay, so before I tell you what the result is, let me just quickly say that this will give you the solution to the exponentiability question. And I want to say quickly, but not entirely the solution I like yet. So it is correct, but it's a little messy. It's a little too big, let's say it that way. So we'll get to that in a moment. So I'm going to make things still, the bicategory fraction still a little smaller because I'm going to make K compact. Otherwise it won't work anyway. And then after that, we will shrink our O map to something a bit smaller, as inspired by Chen, actually. So I need to ask that K be orbit compact, so that the quotient space is compact. I mean, we know from manifolds already that we can only do mapping manifolds if we have a compact domain. And but then once K is compact, I'm going to reduce myself a little further here and take for the generalized maps only the guys that have a finite U. So if you do that, then here comes the result of doing the co-limit construction. So my space of objects will just be the disjoint union of the spaces of objects of G map of K upper star U into G. So for all the different U's, all the different maps from K upper star U into K, that is isomorphic to, an essential covering map. So that's my space of objects. And then for the space of arrows, I need to do a little bit. Oh yeah, and of course, this was compact open topology, but I told you that already. So for the space of arrows, we are working with diagrams of this shape, as I told you earlier. And so what I have to topologize are these triples, phi, beta, psi. Because the rest of this is part of the indexing. So we take a disjoint union over these pairs. Now, since I already had decided that given a pair, I would take this as my pseudo pullback as my square, I don't have to say anything else about that, except that it will show up here in my description of what I need to do. So given an epsilon u and an epsilon v, the right-hand side, so can now be described as maps from phi after pi u to psi after pi v. So how do I get those? Well, so I need a copy of G map K upper star U G naught, that is giving me the phi. So phi lives in this part. And here is another copy of K upper star V that will give me the psi. And what do I need in the middle? Well, beta is a map from the domain space, or sorry, the object space of the pseudo pullback to G. So, but it is, or I can also say it's a natural transformation. So it's an element of G map P epsilon from P into G1. So I could write it as map, but I decided to write it as this because I need to make sure that the beta fits between the phi and the psi. And so I'm taking the pullback over G map PG0, where I take the source coming from the right-hand side and I take pi upper star u as composition with pi u on the left-hand side. And the same thing on the other side, then it's going to be the targets from the one space from P to G, and then pi upper star V to compose psi with pi V before I put it in the right place. So in this way, I also make sure that what I give you is actually a Natta transformation, so that it has the naturality properties and so on. So rather than writing map P to G, which you might be tempted to do, write G map at level 1, and then you have the right thing. So you have the right subspace of map PG. Maybe I should stop here for a moment and ask, are there any questions before I keep running? Everybody still okay? Okay. Okay, so that's, if I do it this way, I do get the right result for the exponentiability. However, I have just created myself a groupoid that's not étale. It's proper, but not étale. And I really would like to have one that is proper and étale. So that I can clearly see that I have an Orbispace, because proper groupoids can be Orbispaces, but they would have to be Morita equivalent to an étale one. So let's double check that is actually possible. And what I need for that is to reduce a little further to what we call admissible generalized morphisms. And the admissible condition is inspired by chance. It's slightly different from chance, but it's kind of morally equivalent, let's say it that way. So I'll call such a span admissible if every open that I used for my open covering is relatively compact. So its closure is compact in G0. And furthermore, I want to say that psi can be extended to that closure. So what I'm really doing, in a sense, is to say I want to take the G upper star on the U bars. So I want to take the, now this is not an étale groupoid anymore. That's the only little problem of that. But that's kind of what you are thinking about. But I can still work with the étale groupoid if I like, as long as I remember, I'm only taking the size that can be extended to the closures. And I only take the ones that have this compact closure. So I can then see that A map, so I'm going to call it A map if we have an admissible span. So this I can take for A map the full subcategory of O map on the admissible spans with finite essential coverings. And then now there are two ways to topologize A map, and the kind of maybe easiest way is the wrong one. You could just say, oh, hey, A map was a subcategory, so why don't you give it a subspace topology? Well, that one doesn't work. So don't take that one. The other one is, of course, the harder one, and actually requires a little bit of choice, because there's also a way of doing it by choosing a shrinkage. So if you take for every open cover a shrinkage that were of essentially compact ones, then I can define the map rho from O map to A map by sending epsilon phi to the shrunken version of it. So I'm now going from O map to A map rather than from A map to O map. That's the point. And so then the topology that would make rho an open map, because you want it to be open, essential equivalence is needed to be open. And that's why this actually gives a topology, determines the topology that I want. It's the one that has its basis opens in terms of the compact subsets of the closures of the U primes and the extensions of phi to these closures. So what I'm effectively doing is taking these other groupoids with the closures, but in order to see that I still have an essentially equivalent mapping groupoid, by doing that, you have to look at it the way I just did. And so if I do that, then the topology on the space of objects becomes kind of what you would expect, I think, now, disjoint union of the G maps from K upper star U bar to G. So realize that I require that the U's without the bars are covering, and then, but then I use the bars when I put the topology on it. And so then the space of arrows, of course, is defined by pullback again. And for the K upper star U bar, if you're wondering how I defined that thing. And if you want to get the space of arrows of the mapping space, I do the same thing I did before. I just have bars sitting everywhere because the corresponding, so if you put a bar here and there, you need to put a bar here as well, which basically means that I'm also taking the closure in K1 for the middle chord. So the wherever needed, you need to take another closure in there to make that all. Closures are all taken within K. And then everything is defined just as before. And this one has the property that it is proper n-atile, and it is the exponent, and it's invariant on the Morita equivalence. I think OMAP was too, by the way. I just forgot to put it in there. Now we need to look at enrichment. So a priori, you might do what we try to do, which is say, oh, composition can be defined on having something in here and there, and I get something there. The only problem is that is not continuous. And so, so at first you were like, oh, it doesn't work. And then he said, wait, maybe we need to make this a generalized map because these are Orbispaces. And so rather than trying to just get a functor, we are allowed to make ourselves a covering. And by doing that, there is actually a covering that will turn this into then something where we have a covering where on each element of the covering, we are able to go continuously across. So, and I should say, again, this only works for orbits compact orbifolds. So we do have to restrict ourselves to that. So what is the essential covering? So if we, so remember, we need to kind of sort out how we want to compose pair spans. And I'm allowed to make epsilon U and epsilon V fixed, because that's kind of giving me a disjoint and a connected component of the space. So it's enough to do it with a given epsilon. Oh, oops. As long as I put my epsilon V in the right place. So I can take the left-hand arrows fixed, but I need to make sure I can then compose well with respect to the right-hand sides. And that requires finding somebody on the top. And so the way we're going to cover this space of two copies of GMAP, a product of two copies, is to say, I am going to choose a W that I might like to put there, a G upper star W, a given cover. And I'm going to, given that cover, say, for which pairs would this be a good cover to use for the composition? So remember, covers only have to be finite today because we're compact or orbit compact. So for every finite, relatively compact essential cover W of G, that is factoring through epsilon U so that I can actually use it. So epsilon V is going to sit here. Such that the images of W in G are relatively compact and in U are relatively compact. So I really want them to sit in there so that their closure is still inside the U as well. So I want this for the W, and I want to have an index function from W that sends every element of W to an element of V. So the U are sitting here and the V is sitting here. And so I take an index function and the W. If I have that, then I can define the following open subsets of G map G upper star U into H cross G map H upper star V into AK. I take all the pairs phi psi such that if I take phi of the closure of an element W in W of its image in G upper star U, because that's where phi is living. Phi is sitting on this one. That needs to end up in the sigma of W, which is an element of V. So you can also, if you like, you can call that VW. That helps you to kind of see it really as an open again. So I'm now asking, actually, I don't ask anything for my psi's. Any psi is fine. But I want the phi's such that phi sends this closed subset to that open. That is defining an subbasis of subsets of the compact open topology. So, because I have only finitely many of them, so this is good. And then if you are working with just this O, it turns out that you can indeed compose these guys by using the G upper star W. And furthermore, because of the way we have set this all up, there's precisely one map that fits here actually, so that's the square commute, which is a bit stricter than what you would usually ask. But because we do that, we can actually see that this is now going to give us a continuous composition. So we're really choosing a very specific composite on that W. And so that actually gives us then the enrichment that I was claiming. So the map is, so the A map is étal and proper. And we furthermore have that we can also enrich over Orbispaces themselves now, basically, as long as we allow composition then also to be an Orbispace map, which was a span. Actually, before I go to examples, are there questions about this? Otherwise, I guess I have a couple minutes left for examples. So first, two kind of basic examples so that I can build the others from. First of all, if there was no non-trivial isotropy, and then a map becomes simply map between the underlying spaces. So we are extending something that people knew about. And furthermore, if we have the opposite end of kind of having just a point with a group G and another point with a group H, so I'll call those star G and star H, then the space of objects is just the discrete set or discrete space of Groupoid homomorphisms from G to H. And the interesting part is the space of arrows. What do we require for the space of arrows? It turns out, if you think about it for a moment, naturality requires you that it's those H's in H so that psi is equal to H phi H inverse, or another way to say it is that it's those group elements in H that sends phi to psi by conjugation. Because your natural transformation can just choose one group element, and that group element by its naturality square has to satisfy this. Okay, so that conjugation is important. That's going to come back. Okay, so let's first look at the rectangular billiard table. That's what you would obtain if you would take just a rectangular grid on R2 and do the reflections on the lines. And so we have basically a rectangular underlying space with reflection boundaries, so Z2 all on the boundary, except for the 4 corner points, which have a Klein-4 group, or Z2 cross Z2. Now, Z2 cross Z2 is the only dihedral group that is abelian. And so conjugation becomes kind of interesting there in the sense that if I now I'm going to look for the maps from P2 into the space. Now, P2 is the point with Z2 action. So I have two choices. I can either just send the whole group to the unit elements in on the codomain, and then I get my ordinary orbifold back. So that is kind of what I see here in the middle. That's the middle component. That is just the orbifold itself. But if I require that my non-trivial group element goes to a non-trivial element on the codomain, then I have to map the point into one of the boundaries. And then if I look at those silvered boundaries, once I put the group element here, like in one of those points, I realize that the isotropy group will by conjugation send the point again to itself. So you automatically get a line with a trivial Z2 action. And on the corners, because there was a full V4 sitting there, that whole V4 comes again in there because everything on the conjugation is itself. And so if I do it on the other sides, I just get the same thing, but the different sides don't connect to each other in that respect. They are separate. And then there is an extra point in the corner because we know that that's V4, the Z2 cross Z2 has an extra element of order 2. So that element again, and that's done again a Z2 cross Z2 point. So that's what we get here. The triangular billiard table goes different. So by the way, this is a part of what we call the inertia groupoid, for those of you who happen to know about that. Oh, not going to triangular yet. But last time I gave this talk, one of my students actually asked me, what would happen if I would map the silvered interval into the billiard table? I said, okay, let me have a look at that. And so rather than trying to describe the whole mapping space, because that's messy, I'm just going to give you connected components. So I think it's connected components, you can think really is kind of like free homotopy. So don't keep your endpoints fixed. And in that case, it's kind of interesting. So what you are going to get, besides the trivial components, which is the space itself is contractible here. So if you don't send the endpoints to Z2 points, then you just get, you know, something that's just homotopy to one point at least. But if you send them to the boundaries and so on, then there's a couple of interesting things you can do. On each one of the corners, you could take that extra element of order 2 and then you could make just a loop into the space and coming back. And that's, you could also start on that special point and then move into one of the boundaries. And I possibly still don't have them all. I just realized, oh yeah, okay, here. So I didn't draw all of them because it was getting too messy. But the idea is that you can go from a corner point to one of the other boundaries as well. And you can go between two boundaries, and you can go from a boundary to the same boundary. And so those are all in different components, but then wherever you are in the given boundary, of course, doesn't matter. So that's the idea. So here, there's quite a bit going on. Now, if you go for the triangular billiard table, it becomes quite different. It's really fun. Because here, again, you would expect your different segments, but if you now look at the endpoints, they are conjugates in D3. Because the sigma 1 and sigma 2 in a D3 are conjugates with the rotation. And that means that these guys get glued together to a full circle. And actually, if you go back to the, what do you call it? The wallpaper group, the wallpaper pattern, you will see that if you do a wallpaper pattern for the rectangular billiard table, and you look at one of the straight lines on the reflection lines, it's always in the same part of the table. It doesn't go through the other parts. If you take a straight line and a triangular one, it moves through all three sides of the table. And there you can already see that there's something going on. And so the orbifold tells you the same thing. These three form a circle, and you can just move through them. And that means that if I now look at the silvered paths into this space, there are only two components. There's a component of everything trivial, and there's the component of start and end on the boundary. But where you go on the boundary doesn't matter. They're all the same. Let's see, how am I doing? So should I be finishing? Or do you want to see one more example? One more example?
Yes, please.
Okay.
Thank you.
This one's kind of fun. Laura and I just sorted this out this weekend. We were like, I was thinking, which wallpaper group is this? And then I was grateful to realize it was the basket weave, which is actually one of my students really likes. She's been studying this with native people, and I'm not sure that she has actually done this aspect of it. So I need to still talk to her about that. So it's kind of fun. Let's look for a moment. What is the group here? Well, we have a cone point of order 4, because you go around like that. Or if you do it here, you can see that as you go here, this line goes to that line. So it's rotated. It's a cone point of order 4 in the middle. And then on the sides, you still have your V4s, your Klein-4 groups. And so it's like a billiard, but with the extra symmetry. And so we have, for the quotient space, I like to take things first to something that I know already, which would be the billiard. So it starts with the billiard and then realize, okay, I have an extra cone point that I need to further cut out. So if I don't think about that, then the way I normally make cones is to make a cut and fold them up over themselves. And so if you do this with some origami paper, it's nice. So you make your triangular cut and you fold them over until you have only one corner left. So we have basically a silvered boundary on the bottom with a Klein-4 corner there and a cone point on the top. The rest is smooth. If I do that line only to kind of help you see that there was a cone there. Okay, so we had already baptized it party hat on Saturday until I realized it was called basket weave. So it's your choice which one you prefer. And if I look at the Z2 points of this one, what do we get? Well, of course, there will be one extra point that I didn't draw. I'm very sad. Oh yeah, wait, here it is. Okay, Z4, there's one point that by taking the element of Z4 that has order 2, and it gets again by conjugation all of Z4 as its isotropy group in the mapping space. Same thing on the bottom here for the special extra reflection in V4. The other two reflections, if you walk around, are connected. So we have the silver, well, the kind of, I sometimes want to call it the double silvered interval, like this is Z2 and the V4s here, but they don't connect to each other because it's the same thing as what you had at the billiard table, at the first billiard table. Okay, so these are the Z2 points. And that makes it interesting now when we go to doing the silvered interval mapping into it, to the silvered paths. So there's a bit more going on here now. For the first one, I also wrote it down in terms of the wallpaper pattern so that you could see it there. So the general idea is I can go from the boundary to itself. That is one. But now it's important whether I go around that cone point or not. So because if you want to contract over the cone, you need to go around 4 times. You cannot contract earlier. So but on the other hand, it doesn't matter where my second point on the boundary is. I can go around. It doesn't matter wherever it is. That's fine. So we have one, and then we have one for one going around. Once going around. That's actually, which one is it? The blue. The blue goes once around. The green goes twice around. Purple goes 3 times around. And let's see. I could maybe make that a little bigger so you can see that better. And then you can do the same thing from the corner with that special point, starting and ending. And also if I have one special point and one of the other on the side, those are all distinct. So that gives me 12 components that have to do with either walking around the cone or not. And then there is also 2 components that just connect the cone to either the special point or the other reflection along the boundary. And that was all that I wanted to tell you today. And here's one more Orbifold that you can play with if you like. Thank you.
Thank you so much for the lovely talk, Dorette.
Thank you, and sorry for going overtime.
Oh no, that was great. Yeah, I wish you would keep going with the examples. Yeah, thank you so much.
I need to get a student to do all the wallpaper groups for me.
Well, are there any questions or comments for Dorette?
I just was wondering, like, if you have these two party hats,
yep.
Like, what happens if you have like 2 of them and you join in like by the bottom or by the top? Like,
so, oh wait, if you want to do it joining via the bottom, that is not entirely an orbifold operation at that point, I guess. Because you would be connecting points. So I'm just wondering, because the bottom is not really a boundary, that's the problem.
Yeah. Okay.
So I've actually been thinking, this is something else that needs to be done, is to describe what does it mean to glue orbifolds. And you have to be super careful. As I said earlier already, like push-outs of Orbispaces generally don't exist. But I've been thinking this is an open research problem that we should look at more carefully as to what kind of gluing and what kind of push-outs can you do for Orbispaces.
Okay.
I think actually, okay, I can give a partial answer at least because I actually calculated such, but I calculated the push-out and I know the push-out is nice at least if you glue along a sub-orbifold. But you have to be careful to define what sub-orbifold means. And doing that mirror is not suborbifold. So that one cannot be done. But that's something that needs a bit more spelling out.
Okay, this thing that you say that if you do the gluing with the suborbifold, it's like this construction you did, like you can see at the diagonals and gluing by that.
So you're thinking of going along here?
I'm trying to imagine, yeah, something like that.
And what is the question then?
Just trying to understand and imagine what happens with gluing and different. If you try to glue different paths, yeah. Like that could be a valid gluing if you take this diagonal, or not. Like.
Okay, I know that it's always, you need to think hard about whether suborbifolds can be, whether something is a suborbifold or not. So this would correspond to basically the line here. And I am...
Maybe this question
it might be okay. I need to think about it a little more carefully, but because this line is at least closed under I'm just wondering whether I might have to take the two. That should be fine because I can do that. I'm wanting to say yes, but I'm not 100% certain.
It is because what I'm thinking is at first you give it a twist that has like order 4, and this is given like an extra twist with another.
Yeah.
Like is it okay?
Yeah, like no, I think, I mean, you get something that doesn't look like a manifold, but that's okay because we had already said Orbispaces were allowed to be more. I'm just wondering how happy we are with kind of a figure 8 coming in there. I think that's okay. I have to think a little more. Well, that seems to be okay. And in that case, so what you would, if you would look for Z2 points, for instance, you would get this more interesting. Oh, now, okay, now the question then becomes, so you go around and you go around the other, and do these talk to each other or not? I think they should. Wait, do they? Oh, so I'm not certain, okay? Because these calculations, you have to be super careful. It's very easy to make mistakes, but you might actually get a full circle on offset 2 points there. But I want to do that calculation one more time before I believe that. It might also be that they just remain completely separate from each other.
Okay. Yeah, thanks. Don't worry. Just I'm curious about this.
This is speculation.
Yeah.
I must say, every time I get questions like that, I want to go solve them. So they're fun. Anybody else?
Thank you very much, Luis. Maybe Carlos can ask this question.
Yes. Yeah, thank you for this nice talk. Yeah. My question is about what happened with the model structure of the category of Groupoid. How is related with
I can say something about that, actually. So because we had, well, actually what I looked at was, I had not looked at the one for Groupoids in general. I looked at the one that Helen Coleman and Christina Costoya had written. It's not published, and there's a reason for that. Although I think they should have published it, but that's my opinion. But so they weren't happy with it because, as you know, orbifolds don't have all pullbacks, and at least if you go for Orbispaces, which they were doing, and they certainly don't have push outs. So they were like, oh, it's not really worth anything. And actually, I think it is worth something because they do have vibrant replacement, and which means that that's another way to get to mapping spaces. And if you take the vibrant replacement version of things, it gives you a mapping space for all pairs of orbifolds in terms of groupoid, and it's small. So because you go vibrant replacement and then take GMAP between the vibrant replacements, and actually that was originally what we were thinking of doing, Laura and I, when we couldn't get this composition to work. And the only issue with it is that, so it's a Heffliger groupoid that they use for that. And so you need choice because you have to choose locally finite subcovers of things, and you end up with a non-compact, scrap that, non-Hausdorff groupoid. So that was the funny thing for us. It's like, oh wait, the problem is that you get a lot of repeats of basically the same map, and the groupoid, the mapping groupoid recognizes that and doesn't separate them. So so I've been wondering, there's this Hausdorffification of a space, and what might be the case, but we haven't sorted this out because we looked at it and then decided to first finish this up because otherwise this paper will never be written. If we keep finding other fun stuff, is that what might be the case is that we simply get a whole bunch of extra copies of parts of the space that are not being distinguished by the topology, and that if we would just collapse them, normally Hausdorffification is kind of an infinite and a transfinite process. It might actually be finite for these spaces, but that's a conjecture, let's say it that way.
Oh.
And so in that sense, this is, and I think in that what we also haven't checked yet is, if you first Hausdorffify, I would hope that you get the correct mapping groupoid back for the guys that are compact. But again, that is totally speculation at this point. I haven't done any we haven't done any calculations on that. We just observed, oh, these things can be non-Hausdorff, which would definitely, that could still be Morita equivalent, by the way, to a Hausdorff one. As long as there is enough stuff connecting those, pieces that are not. So if everybody who is not separable from somebody else is actually connected to that other point, then that could still be okay. But we were like, oh, this is a whole different class of groupoids. We haven't ever looked at non-Hausdorff groupoids, so. So that's all I can say, is that at least with the fibrations and co-fibrations that Coleman and Costoya had or have, is then there is a way of doing mapping spaces. I haven't looked at the other one for group. Is there one for topological groupoids and a model structure?
I guess it's this of the paper or rest that also just configuration are injected in objects, and the fibration are isofibrations. Yeah.
Okay.
Yeah.
I will have a look at that. I haven't looked at that. That might actually be quite interesting to kind of compare what you get there as mapping spaces. And then the question is, of course, if you take a fibrant replacement of an Orbi groupoid, is it still an Orbi groupoid? Are their essential equivalences the same as ours?
Yes, yes. Only I think the model structure works without topology, so maybe.
Okay.
Yeah.
Well, yeah. So I will have to look at what have to look at some of the details. It would be nice, because that would be another way of making mapping groupoids and see what you.
I was thinking that because of this double category of function construction, you was building another homotopy category, but maybe I was wrong.
Well, we do hope to use these for homotopy, for orbifold homotopy, of course, because now we have path spaces and simplicial spaces and stuff that you can build here. And
well,
but yeah, no, we haven't gotten that far yet. We haven't looked yet as to whether this is the path object for a model structure. That's that would be another thing to look at.
Thank you very much.
Thank you very much, Carlos. Are there any other questions or comments?
Shall I stop sharing, perhaps? Can see more faces.
Yep. Well, if not, let's thank Dorette again for the great talk. Thank you.
Thank you for great questions, actually.
And well, of course, let's thank Laura and Martin for coming, for visiting. Well, so as I said, this is the closing session of the Stern seminar. I'm sorry I didn't tell you direct, but that's it. So yeah, thank you everyone for coming to the series, and it's been great, and it was a great closure. Thank you so much. And yeah, we'll see you at ICA hopefully in the summer, and hopefully next term. Yep.
Thank you.
Well, there's a question here, maybe.
No, nothing question. Just thank you.
Yes. Okay.
Yes, thank you.
Yeah, thank you. Well, so yeah, this is it's a somewhat small group at the moment here at UNAM. So Luis is part of it. Carlos, well, Akif is he's in Turkey, but he's a regular at the seminar. Paul as well, and well, student of mine, Ruben. So, and Omar, of course, one of the organizers. So yeah, we're very happy to have you, Dorette.
Thank you. I think I should become a regular here too in the future. If it works out for my classes next semester.
Well, yeah, we'd love to have you.
Paul Perret is a regular.
Yeah. Well, yeah, he said he wasn't able to come this time, but yeah, Bob Perez is usually here.
Bob has seen a good part of this talk, if not all of it, actually. So he just hasn't seen the cool examples. So I think last time I ended at the enrichment. So
well, yeah, he probably missed the best part. Yeah, yeah, that's what he mentioned. He mentioned he had seen most of the talk. Yeah, Luis.
Thank you for the great samples. I think this talk was very incremental. Like when I was thinking about something, like the next slide was explaining that. So it was really good. Thanks.
Oh, thank you.
Yeah, we hope you sometime have you here in Mexico.
That would be nice. Yes, I must say that this was my first sabbatical without doing any travel. Well, I have spoken in quite a number of seminars, but I was just, a friend of mine put something on Facebook about, I don't need any counseling, I just need to go to Jamaica. And yeah, I can give you my list of countries I need to go to. Thank you all.
Well, have you been to, well, not, well, I suppose Jamaica, I don't know, but Mexico?
I have been to Mexico, but to Merida for the IMO